Good morning, everyone. My name is Ng Yi Hong, and I'm with my team members Ngai Ho Yin, Benjamin Ho Kai Keith, and Kao Guo Shen. Today, our team will be presenting on a critical vulnerability in our future telecommunications infrastructure and how we intend to solve it. Our topic is quantum secure inference in 6G satellite networks, mitigating atmospheric and cosmic noise for global quantum security. As we move towards the 6G era, we face a paradigm shift. The threat of store now, decrypt later cybersecurity attacks means that future quantum computers will eventually break our classical method of encryption. To secure 6G, we must rely on quantum key distribution, but doing so from space introduces massive environmental challenges. Now, one huge problem that we face is that the terrestrial fiber optics suffer from exponential signal loss over long distances, making global quantum networks impossible on the ground alone. One solution that is in development currently is SAGIN, the Space Air Ground Integrated Network. By using low Earth orbit satellites and high altitude platforms as quantum relays, we can establish a global unhackable backbone. However, beaming single photons through the Earth's atmosphere is an immense engineering hurdle. Let us see why. To understand this challenge, we must directly address the effect of noise on communication systems. Let's first establish our baseline with these two classical systems: classical analog communications and classic digital systems. In classical analog communications, additive white Gaussian noise, or AWGN, directly degrades signal fidelity or signal quality. It lowers the signal to noise ratio, meaning the output quality simply becomes fuzzy. In classical digital systems, noise forces symbols across decision boundaries. The system performs perfectly until the noise exceeds a specific threshold, at which point the bit error rate or BER spikes and the link fails. However, traditional mitigation like cranking up transmission power or using heavy signal repetition is impossible in quantum mechanics because we cannot clone or amplify an unknown quantum state. We need to see how this noise fundamentally changes when we enter the quantum realm. Hence, I'll now pass the floor to Speaker 2 who will provide said explanation.
Thank you. When we transition from digital bits to quantum qubits, the primary performance metric changes from BER to QBER, the quantum bit error rate. As you can see on the screen, this is the fundamental equation for QBER. It is the ratio of error and noise counts to the total number of detections. The crucial variable here is N, or background noise. In quantum security, we have a hard mathematical limit, the 11% threshold. If environmental noise pushes the QBER above 11%, the errors become completely indistinguishable from the disturbances caused by eavesdropper. At 11.1%, the secure key rate drops to absolute zero. The network is severed. So, what drives this background noise? The primary physical obstacle is the Earth's atmosphere. When a satellite fires a laser down to the ground station, it hits atmospheric turbulence. This causes three major effects. First, scintillations, which is a rapid fluctuations in intensity essentially. The laser twinkles like a star, causing photon counts to drop randomly. Second, beam wander, where large thermal eddies physically push the beam off the receiver lens. And finally, wavefront distortion, which destroys the delicate phase of the photons, completely ruining phase-encoded quantum keys. Beyond the atmosphere, we also face cosmic and hardware noise. During the day, solar background noise, stray photons from the sun, can easily blind our sensitive detectors. Furthermore, the detectors themselves suffer from dark counts, which are false positives triggered by thermal energy rather than actual photons. Finally, simple diffractions over 500 kilometers of space causes massive photon loss. We understand the noise. The question is, how do we defeat it? Speaker 3 will now explain the real-world engineering applications used to mitigate these effects.
Thank you. This brings us directly to course learning outcome 4, describing communication theory through real-world applications. To counteract wavefront distortion, we apply the theory of phase conjugation using a real-world technology called adaptive optics. At the optical ground station, we use a wavefront sensor to measure the exact atmospheric distortion of an incoming pilot laser. This data is fed into a high-speed deformable mirror, seen here on the slide, which physically changes its shapes thousands of times per second. It acts like a dynamic pair of glasses, unblurring the atmosphere and focusing the quantum signal perfectly into the detector. This physical application alone can improve the coupling efficiency by over 20 decibels. But hardware alone isn't enough. We also apply advanced network theory. In 6G architectures, we use deep reinforcement learning, specifically proximal policy optimization, to manage the network. Because clouds and severe turbulence physically block the quantum links, the AI monitors the real-time weather and turbulence data. Instead of suffering link failures, the AI dynamically predicts open atmospheric windows and routes the quantum keys through alternative UAVs or satellite nodes. As the chart shows, this AI optimization pushes the routing success rate from a baseline of 65% up to over 96%. Finally, we apply rigorous filtering theory to eliminate solar background noise. We use spatial filtering, which is tiny pinholes to restrict the receiver's field of view. We also use the spectral filtering, which is optical filters that only allow the exact nanometer wavelength of our laser to pass. And we use temporal gating, which is synchronizing atomic clocks so the detector only turns on for a single nanosecond when the photon is expected. Together, these applications shrink the background noise to near zero, which can keep our quantum bit error rate well below that critical 11% threshold. I will now hand it over to Guoshen to conclude with the global impact of these technologies.
Thank you, Benjamin. By successfully combining adaptive optics, AI routing, and advanced filtering, we achieve our ultimate goal, the 6G quantum backbone. What you see here is the realization of the space-air-ground integrated network. By utilizing low Earth orbit satellites to bounce entangled networks photons across continents and mitigating the atmospheric noise as they re-enter the atmosphere, we completely bypass the distance limitations of fiber optic cable. This is no longer theoretical physics. It is the blueprint for the next decade of global telecommunications infrastructure. Now, the real-world implications of this technology are massive. First, in financial infrastructure, global banking, ledgers, and stock exchanges rely on instantaneous secure data transfers. Quantum secure 6G ensures that even if a bad actor captures the encrypted financial data today, they will never be able to decrypt it with future quantum computers. Second, in defense and government, it provides an unhackable command and control channel for strategic national assets, immune to interception. And third, in autonomous V2X systems, as our smart cities filled with autonomous vehicles, swarms, and drone logistics, quantum secure links prevent catastrophic cyber physical hijacking. The security of the data directly translates to the physical safety of the public. To conclude, achieving quantum secure inference in 6G is fundamentally a battle against environmental noise. As we have demonstrated today, successfully navigating this challenge requires a deep understanding of how analog, digital, and quantum systems react to atmospheric and cosmic disturbance. Furthermore, by taking these theoretical models and deploying real-world engineering solutions such as adaptive optics at ground stations and AI-driven network routing, we managed to bridge the critical gap between communication theory and physical application. The transition to 6G is not just an upgrade in bandwidth or speed, it is a fundamental redesign of global security. By mastering the quantum channel and mitigating noise that threatens it, we can ensure that our future infrastructure remains truly unbreakable against any computational threat. Thank you for your time, attention, and the opportunity to share our research with you today.